Hi there, Science 9 students. I'm going to give you a brief lesson today on multivalent elements. So, just a reminder, you'll find a variety of resources on this topic. I'm just one. What I'm going to do is I'm going to go through some of the example questions from the notes package, and maybe some of them will show up on the handout that I make for this. So again, this is lesson 11, compounds of multivalent metals. So what's a multivalent metal? That is a metal in the periodic table that can have more than one possible ion charge. So you know that if you look in the periodic table, you'll see little boxes and you have the element symbols. And then the top right, you're going to see a little symbol with a plus next to it. If it's just plus, that means it's +1. That means if you make an ion out of that, you're taking off one electron, that gives it a +1 charge. If it says 2+, that means that you can make a stable ion by taking away 2 electrons. If it says 3+, you can make a stable ion by taking away 3 electrons. You can see these examples in the periodic table: +1 sodium, +2 zinc, +3 aluminum. And those are the only numbers that are going to be given for those elements. But other elements, especially those ones in the middle of the periodic table, columns 3 to 12, they're a little more complicated because they can have more than one possible ion charge. If you look at iron, for example, you're going to see a little Fe, and then it's going to say 2+, and then 3+. What it's saying is there's more than one possible charge that iron can have as an ion. You can make a stable ion by taking away 2 electrons, but you can make one as well by taking away 3 electrons. I think the 3+ might be more common. The same is true for, say, copper. You can make a stable ion of copper by taking away 2 electrons or by taking away 1 electron. There are many elements that are like this. Some elements like vanadium and manganese, again, transition metals in the middle of the periodic table, they got lots of possible ions. For vanadium, I think you can take away as many as 5 electrons and still make a stable ion. So this becomes a little bit difficult for chemists when it becomes a question of how do you name the compound and give full information about the ion charges that are involved, because you're going to get different compounds depending on which charge the metal has. It's different to say, oh, I have a compound made of copper and oxygen. If it's a copper with a 1+, you get one compound. If it's copper with a 2+, you get a different compound. So there's actually 2 different compounds made from copper and oxygen. And chemists want to be very specific, and they want to say which one is which. You don't want to leave any mystery about that, because then, when they're saying the chemical name, people won't really know exactly which chemical it is. So there are instructions for this given in your notes, but I'm going to go through again some problems. I did write up some notes on the board here. There might be some extra stuff here that I packed in that might not be worded exactly like that in your notes package. So I'll project to that just now. A multivalent metal. That's better. A metal whose ions can have more than one possible charge. That is, a stable ions. Most of them are transition metals. So copper, columns 3 to 12. Copper is an example. Copper as an element can lose 2 electrons, or it can lose just 1 electron. Now, there's nothing like especially, it's not like a given element, it's not like a given atom of copper is somehow destined to become copper 2+ or copper 1+. No, any atom of copper can become either one. It depends on what it's reacting with and the exact circumstances of the reaction. Copper can become more than one possible stable ion, so copper is multivalent. Now, there's 2 problems you have to address. One is, how do we make the formula? So that formula actually turns out is not too difficult. In a lot of ways, it's easier than making the formula of a binary ionic compound. like say sodium chloride is a simple binary ionic compound where there's only one possible charge on the sodium. Problem with that is if you don't know the charge on the sodium from the name, well, you have to go to the periodic table and find it. It actually is kind of easier giving the formula for the multivalent, the ionic compound with the multivalent metal, because it's all there. It gives you that ion charge. You don't have to go to the periodic table. The question is, in what form is it there? The answer is it's in the form of a Roman numeral. When I was a kid, that used to be, you'd watch movies, and at the end of the movie, there would always be the year that the movie was made. And it wasn't, for some reason, they never did it in just regular, numbers, like, say, 1982 or something like that. They didn't. What they would do is they would use Roman numerals. And so instead of that, it would say MCM, C triple I, whatever. I can't even remember the formula. Triple C, I won't even try. It was difficult because Roman numerals are kind of complicated. They use all kinds of letters. Now, that being said, the Roman numerals you need to remember are, I think, not too difficult. You really only need to worry about two Roman numerals. They are I for 1 and V for 5. That's all. You don't have to worry about all that stuff I couldn't even remember. I is 1, V is 5. Here's what it looks like in case you don't know. So I, as a Roman numeral, means +1. There, it's in the center of the screen. I, 2 I's in a row, is +2. I is +3. You might think that 4 of those I's in a row is 4, but actually no. For 4, it's actually IV. And it's important that I comes before the V. And then, it basically means, the IV means 1 less than 5. Well, 1 less than 5 is 4. And then V is 5. And if you want to know, say, 6, it's VI. 7 is VII. But there are very few compounds where you even need to worry about that. Really high ion charges are relatively rare. Going up to 5 is pretty much as far as you're going to have to go with any compound you're ever going to see in a high school chemistry course. Now, the question again now becomes, how do you give the formula? And so what I told you is that it's actually not too bad because the Roman numeral gives you the charge. The Roman numeral comes after the metal and before the nonmetal in the name. After the metal, before the nonmetal, you got a Roman numeral in the middle. So if it's multivalent, you're going to see a Roman numeral. If it's not multivalent, there won't be a Roman numeral. For example then, sodium chloride. It's just straight sodium chloride because sodium's not multivalent. You don't say sodium 1 chloride. That would be a mistake. Sodium's not multivalent, and so you don't need a Roman numeral. But I can give you some examples of compounds where you do need a Roman numeral. In your notes package, I go through around here for lesson 11, actually the set at the bottom. I say, hey, what's the formula for iron 3 oxide? All right, how about iron 2 oxide? And then I get some compounds of manganese. So I'll just get going. Iron 3 oxide. The iron 3 oxide, the 3 I's there, tells you that the iron in question's got a +3 charge. It's like they give it to you. So this is why I say it's kind of easier than when it's not multivalent. We use the same rules as we use for compounds that aren't multivalent. The question becomes, all right, how do I get a formula where the O's with a -2 charge, because they keep the same charge, the oxides keep the same charge, are balanced in charge with the iron 3 pluses that are there? Well, the answer is you use that lowest common multiple. Lowest common multiple of 2 and 3 is 6. Your positive charge is going to be plus 6. That's going to be, you can divide that into 2 iron 3 plus, and those are your pluses taken care of. Each oxide is a minus 2. You want a minus 6 total charge. I guess you need 3 oxides. So that's how you balance them. And then how do you get the formula? This is more of a reminder. In the formula, we've got 2 irons. So we say Fe2, and we got 3 oxides. So the formula for that is Fe2O3. How about iron 2 oxide? So Fe2O3 was that one. I'm going to leave that there. Now iron 2 oxide is going to have this name here. Iron, and then the Roman numeral 2, and then oxide. Once you know what those Roman numerals mean, again, it makes the problems easier. The iron 2 oxide means we have a 2 plus on our iron. The oxides are always going to be minus 2. There's no such thing as a negative ion that's multivalent. They're all the same charge. It's just the metals. So here, well, actually, this is really simple because the plus 2 of the iron balanced with the minus 2 of the oxide. We don't need any subscripts. So this is just F-E-O. I can't write this morning. F-E-O. That's it. That's the formula for iron 2 oxide. Let's go through our manganese compounds. Manganese 2 oxide, manganese 3 oxide, and manganese 4 oxide. In fact, I have some manganese 4 oxide right here. To make this mildly interesting, I'm going to show you some. This stuff is actually used in photocopiers. In a powdered form, it gives toner its black color for photocopiers. It's not very reactive stuff. Here it is, manganese 4 oxide. Where do we go with this? All right, I'm going to write it over here. I'm going to write it in blue this time. Manganese 4 oxide. Manganese 4 oxide is what that says, and there. It is right here where I wrote it. We need a formula. All right, this one's a little trickier. Why? Because, well, what's that IV thing? Well, a reminder, IV means plus 4. So our manganese ion's got a plus 4 charge. Your oxides always have a minus 2 charge. This is actually kind of handy because we always know 2 plus 2 is 4, don't we? Our negative charges have to balance with the positive charges. Intuitively, then, you can probably know that, all right, I guess I need 2 of those oxides to balance with the plus 4 of the manganese 4 plus, because the positive charges and negative charges must always balance. All right, throw in another oxide, make a formula. In the formula, we only needed 1 manganese, so it doesn't get a subscript. The oxide does because we needed 1, 2 of those to get our formula going, MnO2. You wouldn't really want to say, all right, well, 2 times 4 is 8. You want to use the lowest common multiple method. If you straight multiplied, you would get Mn2O4. That would not be correct. You want it to be the lowest possible terms. MnO2 is the answer. Now let's look at manganese, I think. Yep, manganese 3 oxide. Oh, I wanted to do manganese 2 oxide. Sorry. I'll work up. I'll do manganese 3 oxide next. All right. There's our name, manganese 3 oxide. That Roman numeral 3, so I've got manganese. This is all in your notes package. And then brackets, I, and then oxide. Well, it's very nice because the Roman numeral gives you the charge. You don't need to go to the periodic table because it's already given. Unless you don't know the charge on an oxide. Charge on an oxide is -2, just like everything else in its column. All right. Well, this actually becomes the same problem as the iron 3 oxide because it's got a +3 charge. We need the same subscripts. If we have 2 of the manganese 3 plus and 3 of the oxides, that's going to balance. We're getting +6 from our manganese ions and -6 from our oxide ions. In an ionic compound, the formula, the charge is always balanced. Plus is always balanced with the minuses. I know I've said that a lot of times because I want you to know it. Mn2O3 is it's the formula for that. And then manganese 2 oxide, well, it's just like the iron 2 oxide, isn't it? The only difference here is that we don't put Fe, because Fe is iron, we put Mn. And so manganese 2 oxide is just MnO. Done. Those are formulas for ionic compounds with multivalent metals. How about getting the name? Well, you're doing the same thing, except the exercise is a bit backwards. These tend to cause a bit more difficulty. Hey, the one thing I want to mention is just a reminder, really, don't put the ion charges in your formula. Your formula should not have ion charges in it. And if it's a multivalent, even if it doesn't matter, if it's a multivalent metal, don't put ion charges in your formula. They're not necessary. Let's look at getting the name from the formula. So, a lot of space here. I'm actually going to work on the top of the board because it's easier to see. So here we're dealing with the top of the page. CuCl, CuCl2, we'll do NiI3 because we already did the iron ones. All right, let's get going. What is the name for CuCl? What is the name for CuCl2? Well, here, now you gotta figure out the charges. In CuCl, we have just one chloride. Each chloride's got a -1 charge. We know the charges must always balance. The pluses always balance with the minuses. Well, that's actually not too bad, is it? We just need a Cu plus to balance that. The Cu, the copper, has a +1. So we call this copper 1 chloride. There. That I, the Roman numeral I, tells you the ion charge on that metal. CuCl2, well, we have 2 of these chlorides. I guess we have to balance that with a +2. There's only 1 copper. So I guess that copper, that single copper in the formula must have a +2 charge. So this is copper 2 chloride. For a lot of multivalent metals, some of the charges are relatively rare. Copper 1+ is relatively rare in comparison with copper 2+. So here is some copper 2 chloride right there. Pretty blue-green crystals. I already showed this stuff to you in the ionic in the FLIR lab. All right, that's copper 2 chloride. Let's do the last two. Why not? So we've got the vanadium V2O5 and RHBr3. Just because. And I'll erase these. V2O5 RHBr3. One day, some of you will probably have the periodic table just about memorized, but you probably don't yet, do you? And that's fine. V2O5. Here, you need to go to the periodic table and you find out that V2, or that V, I should say, is vanadium. By the way, some of you might be tempted at this point to say, oh, okay, my subscript is 2, I guess it's vanadium 2 oxide. No, it is not. The 2 tells you how many vanadiums there are in the formula. So, okay, I've got some V's, but I don't know their charges yet. But look at this. I am told that we have 5 oxides in the formula. And we have 2 vanadiums. Well, each oxide is -2. With 5 of them, we have a -10 charge that has to be balanced out. That has to be balanced between 2 vanadium ions. Well, here's the crux, all right? 10 divided by 2 is 5. This means that each of those vanadium ions has actually got a +5 charge. Now, how do we make that into a name? This is just the backwards exercise of what I've already told you. We figured out now that the vanadiums have a +5 charge, so we're going to call this vanadium 5 oxide. Vanadium 5 oxide. This tells us that vanadium, the ions of vanadium in there, have got a +5 charge. How about RHBr3? All right, well, the only one that makes this one a bit more difficult than others is that you might not know these ion charges. Otherwise, it's actually not too bad. Br is bromine. Bromine is a halogen. That's column 17 of the periodic table. Everything in column 17's got a -1 charge, at least for the charges known. So 3 of them gives us an overall charge that's a negative charge of -3. It adds up. -1, 3 of them adds up to -3. That's going to be balanced by +3 of charge. But hey, there's only one I think it's rhodium. Yeah, it is. There's only one rhodium ion to balance that. There's only one of them. It's got to have a +3 charge. And that +3 is your Roman numeral. So this is rhodium 3, and that's 3 I's in a row, bromide. Okay, so I could go on and on reviewing all those problems, but then I would spend a lot longer than I really wanted to spend. I've gone over the key concepts. So you know what a multivalent metal is. You know that non-metals are not multivalent, just the metals. I've gone over if you have a formula for a multivalent metal, how to get the charge, and how to put that into a name. I've gone over if you have a name for a multivalent metal, you'll know the charge, and that allows you to make the formula most efficiently. So that's everything I wanted to review today, and I haven't done it yet, but I'll get up for you a worksheet. Oh yeah, I was going to show you this too. A lot of these, a lot of transition metals like this cobalt 2 chloride have nice, pretty crystals. So that's kind of nice to see. Hope you have a good day, and I hope this is helpful.